Tonight Earth seems still, but at this very moment Earth is spinning, orbiting the Sun, racing around the Milky Way, and moving through the universe at speeds almost impossible to imagine. In the next few minutes, this journey follows our planet across multiple layers of cosmic motion, revealing just how fast everything around us is really travelling through space. From the rotation beneath our feet to the motion of our galaxy through the vast cosmic web, every second is part of an extraordinary voyage that never stops. Before beginning this incredible journey through the universe, take a moment to like the video, subscribe to Cosmic Bedtime Stories, and join us for more relaxing explorations of science, space, and the wonders of the cosmos. Now, as the stars slowly emerge overhead, the story begins with a simple question. How fast are we really moving through space? The answer is far more astonishing than most people realize. The structure of the large-scale space is defined by a gradual expansion that shapes the motion of galaxies across immense distances. This expansion is not an explosion from a single center, but a continuous stretching of space itself, observed across the universe through the systematic increase in separation between distant galaxies. On the largest scales, matter is distributed in a web-like structure made of filaments, clusters, and vast empty regions. Galaxies are embedded within this cosmic web, and their motion reflects both the expansion of space and the gravitational interactions within local structures. The expansion becomes more significant over distances where gravity is too weak to bind systems together, allowing galaxies to drift apart in a smooth and measurable pattern. At these scales, space is described as dynamic rather than static. The fabric of space-time expands uniformly, carrying galaxies along with it. This motion is not experienced locally within galaxies because gravitationally bound systems hold themselves together against the stretching effect. Stars, planetary systems, and galaxies maintain their internal structure, while the separation between galaxy clusters increases over time. Observations of distant galaxies show that light from them is shifted toward longer wavelengths, a phenomenon known as redshift, which reflects the increasing distance as space expands during the light's journey. This redshift provides a measurable record of cosmic expansion and reveals that the universe has been changing in scale for billions of years. The rate of expansion is described by a relationship between distance and recession speed. The farther a galaxy is from an observer, the faster it appears to move away. This relationship is consistent across large regions of space and forms the basis of modern cosmology. The expansion rate is not uniform in effect on all structures, because local gravitational forces modify motion at smaller scales. Within galaxy clusters, gravitational attraction can overcome expansion, keeping systems bound together even as the broader universe continues to stretch around them. This balance between expansion and gravity creates a layered structure of motion where local stability exists within a globally expanding framework. The energy content of the universe influences how expansion behaves over time. Matter radiation, and a form of energy associated with space-time itself, all contribute to the overall dynamics of expansion. Current observations indicate that the expansion of the universe is accelerating on very large scales. This acceleration is inferred from measurements of distant stellar explosions and the distribution of galaxies across space. The cause of this acceleration is not fully understood, but it is treated as a fundamental property of spacetime in modern cosmological models. It shapes how rapidly distant regions move beyond observable reach over extremely long timescales. Within this expanding environment, galaxies are not fixed points, but evolving systems embedded in motion. Each galaxy participates in both local gravitational behavior and the global expansion of space. In dense regions, galaxies may collide or merge under mutual attraction, forming larger structures. In less dense regions, galaxies drift apart more freely carried by the stretching of space-time. This dual behavior creates a universe that is simultaneously structured and dynamic, where motion depends on both local mass distribution and large-scale geometric expansion. The observable effects of this expansion are measured through precise astronomical instruments that track the position and motion of distant objects. These measurements confirm that space itself changes scale over time, rather than galaxies simply moving through a static background. The distinction is important because it defines the nature of cosmic motion at the largest level. Instead of objects traveling through space, the space between objects increases, altering the overall geometry of the universe. This perspective allows scientists to model the universe as a dynamic system, governed by consistent physical laws. The cosmic expansion field also defines a reference framework for motion at extreme scales. By observing the uniformity of background radiation that fills the universe, scientists identify a baseline state of motion relative to which all large-scale movement can be measured. This background radiation is a remnant of the early universe and provides a nearly uniform glow across all directions. Slight variations in this background reveal subtle motion through space, confirming that the universe has a preferred frame of reference defined by its earliest observable state. As space expands, the structure of the cosmic web becomes more diffuse over time. Filaments stretch, voids grow larger, and clusters remain as the primary regions of gravitational cohesion. This evolving structure reflects the interplay between expansion and gravity across billions of years. The universe does not expand uniformly in appearance because matter is unevenly distributed, but the underlying metric of space-time expands in a consistent manner everywhere. This consistency ensures that the large-scale behavior of the universe remains predictable within current physical models. On the largest observable scale, motion through the universe is not simply a matter of velocity in space, but a combined effect of spatial expansion and gravitational structure. Every galaxy participates in this motion, embedded within a vast and slowly evolving geometry. The sense of speed at this level is tied not to local movement, but to the changing scale of space itself, which defines how distances grow across cosmic time. This expansion forms the outermost layer of motion in the universe, setting the stage for all subsequent layers of structure and movement that exist within it. Motion relative to the cosmic microwave background provides a fundamental reference for understanding how fast the solar system and its galaxy move through the universe. The cosmic microwave background is a faint, nearly uniform radiation field that fills all of space, originating from the early universe, when matter and radiation first decoupled, and light began traveling freely across expanding space. This radiation forms a nearly isotropic glow in all directions, with only extremely small variations in temperature that reflect ancient density differences in the early cosmos. Because of its uniformity, it serves as a stable cosmic reference frame against which large-scale motion can be measured. As the solar system moves through space, this motion slightly distorts the cosmic microwave background. In the direction of travel, the radiation appears marginally warmer, while in the opposite direction it appears slightly cooler. This effect is known as a dipole anisotropy. It does not arise from changes in the background itself, but from the relative motion of the observer through it. The measurement of this dipole allows scientists to calculate the velocity of the solar system relative to this universal reference frame with high precision. The result shows that the solar system is moving at hundreds of kilometers per second relative to the cosmic microwave background. This motion is not isolated to the solar system alone. It reflects the combined movement of the Milky Way within its local environment and the larger scale motion of the surrounding galaxy group and supercluster. Each level of structure contributes to the total observed velocity. The Milky Way orbits within the local group of galaxies, which itself is drawn toward larger gravitational structures. These layered motions combine to produce a single resultant velocity vector relative to the background radiation field. The cosmic microwave background therefore acts as a cosmic benchmark that integrates all these contributions into one measurable quantity. The dipole pattern observed in the radiation field is extremely subtle, requiring precise instrumentation to detect. The temperature differences involved are on the order of thousandths of a degree. Despite this small magnitude, the signal is consistent across the entire sky and provides a reliable measure of motion. The uniformity of the background in all other directions confirms that the observed variation is due to motion rather than intrinsic fluctuations in the radiation field itself. This distinction is important because it allows motion through space to be separated from the structure of space itself. The existence of a preferred reference frame defined by the cosmic microwave background does not contradict the principles of relativity on local scales. Instead, it emerges from the large-scale structure of the universe and its thermal history. In local physics, all inertial frames are equivalent, but at cosmological scales the relic radiation provides a natural frame tied to the early conditions of the universe. This frame becomes useful for describing motion across vast distances where gravitational influences from multiple structures overlap. The measured motion relative to the cosmic microwave background reveals that the Milky Way is not stationary within the cosmic environment. It is carried along by the gravitational influence of surrounding mass concentrations, particularly large galaxy clusters and superclusters. These structures shape the flow of matter on scales far larger than individual galaxies. The resulting motion is smooth on large scales, but composed of many smaller gravitational interactions layered together over time. The interpretation of this motion also connects to the history of the universe. The cosmic microwave background represents a snapshot of the universe when it was much younger and more uniform. As the universe evolved, small density fluctuations grew into galaxies, clusters, and the cosmic web. The motion observed today is partly a consequence of this growth of structure, as matter gradually moved toward regions of higher density. The present velocity of the solar system reflects billions of years of gravitational evolution acting on these initial conditions. The measurement of this motion provides insight into the large-scale energy distribution of the universe. It helps confirm models of cosmic structure formation and the role of dark matter in shaping gravitational flows. Although dark matter is not directly observed, its influence is inferred through the way galaxies and galaxy clusters move. The alignment of observed motion with predicted gravitational fields supports the existence of an unseen mass component that guides large-scale dynamics. On the scale of human perception, this motion is entirely imperceptible. The solar system Earth and all local structures move together through space, without any internal sensation of velocity. Only through observation of distant radiation can this motion be detected. This highlights the difference between local experience and cosmic scale measurement. Motion becomes meaningful only when compared against a stable external reference, and in this case the cosmic microwave background provides that stability. As measurements improve the precision of this velocity, determination becomes increasingly refined. The observed dipole not only confirms motion, but also helps map the distribution of mass in the nearby universe. Variations in motion across different regions can indicate gravitational influences from structures beyond direct observation. In this way, the cosmic microwave background serves both as a reference frame and as a diagnostic tool for understanding the large-scale environment through which the Milky Way travels. The motion of the Milky Way is not isolated but embedded within a much larger gravitational structure known as the Laniakea region, a vast supercluster framework that defines how galaxies flow through space on scales spanning hundreds of millions of light-years. Within this structure, motion is not random but guided by subtle gradients in gravitational potential created by the uneven distribution of matter. Galaxy clusters, filaments, and voids form an interconnected network in which matter slowly migrates toward regions of higher density. The Milky Way participates in this motion as part of a larger collective flow shaped by the combined mass of surrounding structures. This large-scale flow is often described as a cosmic river of galaxies. It is not a physical current in a fluid, but a pattern of motion, arising from gravity acting over enormous distances. Each galaxy follows a path determined by the cumulative gravitational pull of many distant structures rather than a single dominant source. The Laniakea region itself is defined not by a rigid boundary, but by the direction of motion of galaxies within it all converging toward a central attractor region. This attractor is associated with a concentration of mass that influences motion across a wide volume of space. Within this framework, the Milky Way is carried along as part of a coherent flow toward this gravitational basin. The velocity of this motion is measured relative to the cosmic microwave background, but its direction is shaped by the distribution of nearby galaxy clusters and superclusters. The motion is slow on human timescales, but significant when considered over millions of years. It represents a persistent drift through intergalactic space guided by the curvature of space-time, produced by large concentrations of matter. The structure of Laniakea is not sharply defined in the way a solid object has boundaries. Instead, it is identified through the analysis of velocity fields of galaxies. By mapping how galaxies move relative to one another, scientists reconstruct the underlying gravitational landscape. Regions where motion converges indicate gravitational basins, while regions where motion diverges correspond to voids where matter is less dense. This method reveals a hidden architecture of the universe that is not visible through light alone but through the dynamics of motion. The Milky Way's path within this structure is influenced by multiple competing gravitational pulls. Nearby galaxy clusters exert significant influence, but more distant structures also contribute to the overall flow. The combined effect produces a smooth trajectory over vast timescales. This trajectory is not a straight line, but a gentle curve shaped by the evolving distribution of matter. As cosmic expansion continues, the relative influence of distant structures changes, slowly altering the flow pattern over billions of years. The concept of a supercluster flow emphasizes that motion in the universe is hierarchical. Smaller systems are embedded within larger ones, each level contributing to the overall dynamics. Stars orbit within galaxies, galaxies orbit within clusters, and clusters move within superclusters. Each layer adds a component to the total motion observed at any given point. The Milky Way's movement through Laniakea is one such layer sitting above galactic rotation and below the largest cosmic expansion scale. The gravitational attractor that defines the direction of Laniakea flow is not a single compact object, but a region of enhanced mass concentration. It includes multiple galaxy clusters and surrounding matter distributed across a wide area. The gravitational influence of this region extends far beyond its visible boundaries, shaping the motion of galaxies across a large portion of the local universe. The exact nature of this attractor is still studied through increasingly precise mapping of galaxy velocities and distributions. As galaxies move through this environment, their motion is influenced not only by gravity, but also by the expansion of space. On the larger scales, expansion tends to separate structures, while gravity pulls them together. The interplay between these two effects creates the observed flow patterns, In regions of high density, gravity dominates and structures remain bound. In lower density regions, expansion dominates and matter drifts apart. The Laniakea flow exists in a transitional regime where both effects shape motion simultaneously. The Milky Way's participation in this flow is continuous and unnoticeable from within the galaxy itself. Local gravitational binding keeps the solar system stable, while the larger motion of the galaxy unfolds over immense timescales. This separation of scales allows complex motion to exist without disrupting local structure. The galaxy remains intact even as it moves through a dynamic cosmic environment. The study of supercluster motion provides insight into the distribution of unseen mass in the universe. Observed velocities often exceed what would be expected from visible matter alone, suggesting the presence of additional mass-influencing gravitational flow. This supports the existence of dark matter, which contributes to the gravitational framework without emitting light. The Laniakea structure therefore serves as both a map of motion and an indirect map of mass. Within this vast framework, the Milky Way's journey is part of a broader cosmic evolution. Over time, galaxies may merge, clusters may grow, and voids may expand. The flow of matter continues to reshape the large-scale structure of the universe. Yet on any given moment, the motion remains smooth and gradual, governed by the persistent influence of gravity across immense distances. The Laniakea region represents one of the largest coherent structures of this kind, capturing the subtle but continuous movement of galaxies through the cosmic landscape. Within the local group, motion becomes more tightly bound and structurally defined as gravitational forces dominate over the expansion of space. The local group is a small collection of galaxies including the Milky Way, Andromeda, and numerous dwarf galaxies, all held together by mutual gravity. At this scale, space does not expand in a way that separates the members of the group, because the gravitational attraction between them is strong enough to maintain cohesion. The motion within this system is therefore governed primarily by orbital dynamics rather than cosmic expansion. The Milky Way and Andromeda are the two largest members of the local group, and their interaction defines much of the group's internal motion. Both galaxies are moving toward each other under mutual gravitational attraction, following a long, slow trajectory shaped by their combined mass and the distribution of dark matter that surrounds them. This motion is not a simple straight-line approach, but a complex gravitational dance influenced by the presence of other nearby galaxies and the extended halos of invisible matter that envelop each system. Andromeda's approach toward the Milky Way is measured through precise observations of its light, which shows a consistent blue shift indicating motion toward the observer. This motion is slow on human timescales, but significant over cosmic time, with the two galaxies expected to interact more closely in the distant future. The gravitational field between them extends across a vast region of space, influencing the motion of smaller galaxies within the local group and shaping the overall structure of the system. Within this environment, dwarf galaxies orbit in complex paths around the larger galaxies. Some are bound to the Milky Way, moving in elongated orbits that take them through the galactic halo, while others are influenced by both major galaxies and move along transitional trajectories. These smaller systems provide important information about the distribution of mass within the local group, especially the presence of dark matter, which extends far beyond the visible boundaries of galaxies and governs much of the orbital behavior. The local group itself is not isolated in space, but is part of a larger gravitational environment. However, within its boundaries, internal motion dominates over external influences. The gravitational binding energy of the group ensures that its members remain connected despite the expansion of the universe at larger scales. This creates a stable but dynamic system where galaxies continue to move relative to one another, while remaining part of a coherent structure. The motion of the Milky Way within the local group is influenced strongly by Andromeda's mass, which is slightly greater than that of the Milky Way. This imbalance creates a shared centre of mass located in the space between the two galaxies, around which both systems effectively orbit. This barycentric motion is subtle, but fundamental to understanding how the local group evolves over time. It defines the internal geometry of the system and sets the stage for future interactions between its largest members. As galaxies move through this shared gravitational field, their paths are shaped by both long-range attraction and short-term perturbations caused by nearby objects. The result is a dynamic but predictable system, governed by classical gravitational physics extended over large distances. The interactions are slow, unfolding over hundreds of millions of years, yet they steadily reshape the configuration of the local group. The distribution of dark matter plays a crucial role in stabilizing this structure. Observations of galactic rotation and orbital motion indicate that visible matter alone cannot account for the gravitational forces required to hold the local group together. Instead, an extended halo of unseen mass surrounds the galaxies, influencing their motion and ensuring the stability of their orbits. This dark matter framework extends well beyond the visible edges of galaxies and forms the underlying scaffold of the system. The future evolution of the local group is governed by these gravitational interactions. Over extremely long timescales, the Milky Way and Andromeda are expected to merge into a single larger galaxy, reshaping the structure of the group entirely. This process will unfold gradually with repeated close passes and orbital adjustments before final coalescence. During this time, smaller galaxies may be absorbed, disrupted, or redistributed within the evolving system. Despite this ongoing motion, the local group remains a relatively stable region compared to the larger cosmic environment. Its gravitational cohesion ensures that it resists the outward pull of universal expansion. Within this bounded system, motion is cyclical and interconnected, with galaxies tracing complex paths determined by mutual attraction. The local group thus represents a mid-scale structure in the hierarchy of cosmic motion, bridging the gap between individual galaxies and the vast supercluster flows that surround it. Within the Milky Way, motion becomes more structured and confined as stars, gas, and dark matter revolve around a shared galactic center. The galaxy is a vast rotating system composed of hundreds of billions of stars embedded within a flattened disk, a central bulge, and an extended halo. At this scale, motion is dominated by gravity generated by the combined mass of visible matter and an extensive distribution of dark matter that extends far beyond the luminous regions. The solar system is one small component of this rotating structure, following a stable orbital path within the galactic disk. The orbit of the solar system around the galactic center is not a simple circle, but a gentle, slightly elliptical path influenced by the uneven distribution of mass within the Milky Way. This orbit takes hundreds of millions of years to complete, during which the solar system travels through different regions of the galaxy, including spiral arms where star formation is more active and interarm regions where stellar density is lower. The motion is smooth and continuous, governed by the gravitational potential of the entire galaxy rather than any single central object. At the core of the Milky Way lies a compact region of extreme density containing a supermassive black hole surrounded by dense star clusters and gas clouds. This central mass plays a significant role in shaping the orbital dynamics of nearby stars, but at the distance of the solar system, its influence is part of a broader gravitational field created by the entire galactic structure. The galaxy's rotation curve shows that stars at different distances from the center orbit at speeds that cannot be explained by visible matter alone, indicating the presence of an extended dark matter halo that dominates the galaxy's mass distribution. The solar system's velocity around the galactic center is substantial on human scales, amounting to hundreds of kilometers per second. Despite this high speed, all local structures within the solar system remain stable because they share the same orbital motion. Planets, moons, and smaller bodies move together as part of a single gravitationally bound system. This shared motion means that no internal sensation of speed is experienced, even though the system is traveling through space at significant velocity. As the solar system orbits the Milky Way, it also moves vertically through the galactic plane in a slow oscillation. This motion takes it above and below the central disk over long periods, influenced by the gravitational restoring force of the galaxy's mass distribution. This vertical movement adds another layer to the overall motion, creating a three-dimensional trajectory that combines rotation around the center with gentle up and down oscillations through the galactic environment. The structure of the Milky Way is not static. Spiral arms are regions of higher density that move through the disk as density waves rather than fixed structures. As the solar system passes through these regions, it encounters varying levels of gas dust and star-forming activity. These variations do not significantly alter the solar system's orbit, but contribute to the broader environmental context of its motion. The galaxy's spiral pattern itself is a dynamic feature shaped by gravitational interactions within the disk. Dark matter plays a central role in maintaining the stability of galactic rotation. Without it, the observed orbital speeds of stars would not remain consistent with distance from the galactic center. The presence of an extended dark matter halo ensures that the gravitational force remains sufficient to bind the galaxy together even at its outer edges. This invisible structure governs the overall motion of stars and gas throughout the Milky Way. The Milky Way's rotation is not rigid but differential, meaning that different parts of the galaxy rotate at different speeds. Inner regions complete orbits more quickly than outer regions, leading to a gradual winding effect in the spiral structure. This differential motion contributes to the long-term evolution of the galaxy's shape and distribution of matter. Over time, gravitational interactions between stars and molecular clouds further modify the structure of the disk. Within this rotating system, local stellar neighborhoods remain relatively stable. Stars near the Sun move in similar orbits with only slight variations in velocity, maintaining a loosely coherent region of space. These local dynamics allow planetary systems to remain undisturbed over long periods, despite the galaxy's large-scale motion. The solar system's stability is therefore a result of both local gravitational binding and its shared orbital motion around the galactic center. The Milky Way itself is part of a larger hierarchy of motion, but within its boundaries it defines the primary frame of reference for stellar movement. All stars within the galaxy participate in this rotation, embedded in a complex gravitational field shaped by visible and invisible matter. The motion of the solar system around the galactic center represents one of the most fundamental layers of cosmic movement, linking local planetary dynamics to the structure of an entire galaxy. Beyond the spiral structure of the Milky Way's disk lies a more diffuse and less dense environment, known as the interstellar medium, where motion continues in a gentler but still structured form. This region is filled with extremely thin gas dust particles, magnetic fields, and cosmic rays that drift through space between stars. Although the density is far lower than anything found on Earth, this medium still participates in the overall motion of the galaxy. It is not static, but constantly shaped by stellar winds, supernova remnants, and the gravitational field of the Milky Way as a whole. The solar system moves through this interstellar medium as part of its galactic orbit, passing through regions of varying density and temperature. Some regions contain hotter, more ionized gas, while others are colder and denser, forming clouds of hydrogen that can eventually become sites of star formation. The transition between these regions is gradual, and the solar system's passage through them occurs over thousands of years, creating subtle changes in the surrounding space environment without affecting the internal stability of the planetary system. The local bubble is one such region through which the solar system currently travels. It is a cavity of relatively low-density gas created by ancient supernova explosions that cleared out surrounding material. Within this bubble, the interstellar medium is thinner and hotter than average, filled with highly ionized particles. This environment reflects past energetic events rather than present active processes, yet it continues to influence the conditions through which the solar system moves. The boundaries of this bubble are irregular, shaped by past shock waves that pushed material outward into surrounding regions. Motion through this medium is not experienced directly, but can be inferred through the interaction of solar wind with interstellar particles. The heliosphere, a vast bubble of charged particles driven by the Sun, acts as a protective boundary that deflects much of the incoming interstellar material. As the solar system travels through different regions of the interstellar medium, the shape and extent of this heliospheric boundary adjust in response to external pressure. This creates a dynamic interface between solar influence and galactic environment. The interstellar medium is not uniform. It contains a complex mixture of phases including cold, dense clouds, warm partially ionized gas, and hot diffuse plasma. Each phase moves under the combined influence of gravity-magnetic fields and energy input from stellar processes. Supernova explosions inject energy into this medium, driving shock waves that compress and heat surrounding gas. These processes contribute to a constantly evolving structure in which matter is redistributed across large distances within the galaxy. The motion of gas and dust in this environment is slow on human timescales, but significant over millions of years. Material gradually drifts toward regions of higher density, where it may eventually collapse under gravity to form new stars. At the same time, energetic events disperse material back into space, maintaining a continuous cycle of matter within the galaxy. This cycle is a key component of galactic evolution, linking stellar life cycles to the broader motion of interstellar matter. Magnetic fields permeate the interstellar medium and influence the motion of charged particles. These fields are weak compared to those on Earth, but extend over vast regions of space. They guide the movement of cosmic rays and shape the structure of interstellar clouds, contributing to the formation of filamentary structures within the gas. The interaction between magnetic fields and gas dynamics adds another layer of complexity to the motion within this region. The solar system's movement through the interstellar medium is steady but not uniform in its external conditions. Variations in density and magnetic structure can affect the heliosphere over long timescales, subtly changing how interstellar material interacts with the outer regions of the solar system. These effects are small compared to the stability of planetary orbits, but are important for understanding the broader environment of space surrounding the Sun. The local bubble itself is embedded within a larger network of interstellar structures shaped by past generations of stars. Its formation is linked to multiple supernova events that occurred over millions of years, leaving behind a cavity surrounded by denser walls of gas. These structures are not fixed but evolve slowly as the galaxy continues to rotate, and stellar processes inject new energy into the medium. The solar system's passage through this region is one moment in a long sequence of galactic environmental changes. Within this diffuse medium, motion is less about organized orbital paths and more about gradual drift influenced by large-scale forces. The interstellar medium acts as a transitional layer between the structured motion of stars within the galactic disk and the broader gravitational flow of the galaxy as a whole. It represents a region where matter is loosely bound, continuously reshaped by both internal processes and external gravitational influence, forming a dynamic but subtle component of the galaxy's overall motion. Beyond the diffuse interstellar medium and the local bubble, the solar system's motion becomes defined by its interaction with the heliosphere, a vast region of space dominated by the outward flow of charged particles from the Sun. This region is not a fixed boundary, but a dynamic structure shaped by the balance between the solar wind and the surrounding interstellar environment. It extends far beyond the orbit of the outer planets, forming a protective bubble that moves through the galaxy along with the solar system. Within this structure, motion is governed by the continuous expansion of solar plasma and its interaction with incoming galactic material. The heliosphere forms a natural interface between solar influence and interstellar space. It is created by the solar wind, a steady stream of charged particles emitted by the Sun, which travels outward in all directions at high speed. As this flow expands, it eventually encounters the pressure of the interstellar medium slowing down and forming a boundary region where the two environments interact. This boundary is not smooth or uniform, but shaped by variations in magnetic fields, particle density, and external pressure from the surrounding galactic environment. Within the heliosphere, the solar system exists in a region dominated by solar magnetic influence. The charged particles carried by the solar wind form a large-scale structure that extends far into space, carrying the Sun's magnetic field along with it. This creates a protective environment that shields the inner solar system from a significant portion of high-energy cosmic radiation originating from outside the galaxy. The structure of this region is constantly changing, influenced by variations in solar activity and the conditions of the surrounding interstellar medium. As the solar system moves through space, the heliosphere itself is carried along, maintaining its shape relative to the flow of interstellar material. This creates a dynamic balance in which the heliosphere is compressed on the leading side of motion and extended on the trailing side. The result is an asymmetrical structure that reflects the direction of travel through the galaxy. This shape provides information about the relative velocity of the solar system through the local interstellar environment. The outer boundary of the heliosphere is defined by a transition region, where the solar wind slows and becomes turbulent as it interacts with interstellar particles. This region marks the beginning of true interstellar space, where the influence of the Sun diminishes and galactic conditions become dominant. Spacecraft that have crossed this boundary have directly measured the properties of the interstellar medium, confirming its low density and high energy particle environment compared to the interior of the heliosphere. The motion of the heliosphere through space is not independent, but directly tied to the orbit of the solar system around the Milky Way. As the solar system moves through different regions of the galaxy, the heliosphere encounters varying interstellar pressures, which in turn alter its shape and structure. Denser regions compress the boundary, while more rarefied regions allow it to expand. This continuous adjustment reflects the changing environment through which the solar system travels over long timescales. The structure of the heliosphere also reveals information about magnetic fields in interstellar space. As the solar magnetic field interacts with the galactic magnetic field, complex patterns of turbulence and reconnection occur at the boundary. These interactions influence the flow of charged particles and contribute to the formation of regions of enhanced or reduced particle density. The heliosphere therefore acts as a natural probe of the surrounding galactic environment. Within this region, motion is layered across multiple scales. The solar wind expands outward from the Sun, the heliosphere moves through the interstellar medium, and both are embedded within the larger orbital motion of the solar system around the galaxy. Each layer contributes to the overall dynamic structure of space in this region. The result is a nested system of motion, in which local and galactic forces operate simultaneously without disrupting one another. The stability of planetary orbits within the heliosphere remains unaffected by these large-scale motions. Gravitational binding within the solar system is strong enough to maintain stable orbits, despite the external flow of interstellar space. The heliosphere functions as a buffer zone moderating the direct influence of galactic radiation and interstellar particles. This protective role is a consequence of the Sun's continuous emission of plasma, which creates a self-sustaining barrier against the surrounding environment. As the solar system continues its journey through the galaxy, the heliosphere provides a record of external conditions encountered along the way. Changes in its structure reflect variations in interstellar density magnetic fields and cosmic radiation levels. These variations occur gradually over time, corresponding to the solar system's passage through different galactic regions. The heliosphere thus serves as both a boundary and a record of motion through interstellar space. Inside the broader structure of the solar system, motion becomes defined by the subtle balance of gravitational forces that govern the relationship between the Sun and all surrounding bodies. At the center of this system is not a fixed point but a shifting barycenter, the shared center of mass around which all objects in the solar system effectively move. This barycenter is not always located within the Sun itself. It shifts continuously depending on the positions of the largest planets, especially Jupiter and Saturn, whose mass exerts a strong influence on the system's internal balance. The solar system, therefore, does not orbit a stationary sun in a strict sense, but rather a dynamic gravitational center that changes over time. The motion of the Sun around this barycenter is subtle but continuous. It traces a complex path influenced by the combined gravitational pull of all planets. This motion is not large compared to the scale of the solar system, yet it reflects an important principle. Every object with mass contributes to the overall structure of motion. The Sun, despite containing nearly all the mass of the system, still responds to the presence of orbiting planets. This mutual interaction creates a system in which no single object remains completely stationary. The barycenter itself moves through space as the solar system orbits the Milky Way. This creates a layered motion in which local gravitational dynamics are embedded within larger galactic movement. The solar system's internal center of mass follows a smooth path around the galaxy, while simultaneously undergoing small oscillations caused by planetary interactions. These combined motions produce a trajectory that is both stable and continuously evolving. Jupiter plays a dominant role in shaping the barycentric motion due to its large mass relative to other planets. Its gravitational influence is strong enough to shift the center of mass outside the Sun's surface at times. As Jupiter moves along its orbit, it causes the barycenter to shift in response, creating a gentle wobble in the Sun's motion. Saturn, along with other gas giants, adds additional complexity to this pattern, reinforcing the dynamic nature of the system's internal structure. The planets themselves follow elliptical orbits around this shifting center of mass. These orbits are stable over long timescales, maintained by the balance between gravitational attraction and inertial motion. Each planet contributes to the overall gravitational field of the system, even though their individual masses are small compared to the Sun. The interactions between these bodies produce slight perturbations in their orbits, which accumulate over long periods but remain within predictable limits due to the overall stability of the system. The concept of motion within the solar system must therefore account for multiple interacting reference points. There is no absolute fixed center. Instead, motion is relative to the barycenter, which itself is in motion. This nested structure of movement reflects the broader principles of celestial mechanics, where systems are defined by mutual gravitational interaction, rather than absolute positions in space. The solar system is a self-organizing gravitational system embedded within larger galactic motion. The stability of planetary orbits depends on long-term gravitational equilibrium. Although individual planets exert small influences on one another, the overall configuration remains stable due to the distribution of angular momentum across the system. This balance ensures that planets maintain consistent orbital paths over billions of years, despite continuous small-scale variations. These variations contribute to the complexity of orbital dynamics, but do not disrupt the fundamental structure of the system. As the solar system travels through the galaxy, its barycentric motion remains consistent relative to local gravitational forces. External influences from passing stars or molecular clouds are rare and typically weak, allowing the internal structure of the system to remain intact. However, over extremely long timescales, such external interactions can introduce small changes in orbital configurations, gradually altering the system's internal dynamics. The barycenter framework also provides insight into how motion is distributed across the system. It reveals that motion is not centered on any single object, but shared across all components. Each planet, moon, and minor body participates in the collective gravitational structure, contributing to the overall dynamics of the system. This shared motion is what allows the solar system to function as a coherent unit within the larger galaxy. In this way, the solar system represents a tightly bound gravitational system embedded within multiple larger scales of motion. Its internal barycentric dynamics form one layer in a hierarchy that extends from planetary orbits to galactic rotation and ultimately to cosmic expansion. Each level interacts with the others without disrupting the stability of the system, creating a nested structure of motion that defines the behavior of matter on different scales. Within the solar system's broader motion, Earth's path around the Sun forms one of the most stable and well-defined components of planetary dynamics. Earth moves in an elliptical orbit governed primarily by the gravitational influence of the Sun, with small perturbations introduced by other planets, and the shifting solar system barycenter. This orbit defines the year and provides a consistent framework for understanding Earth's velocity through space at a local scale. The motion is continuous, smooth, and largely unaffected by external galactic forces due to the strong gravitational binding of the solar system. Earth's orbital speed varies slightly depending on its position along the elliptical path. When Earth is closer to the Sun, it moves faster due to stronger gravitational attraction, and when it is farther away, it moves more slowly. This variation follows the conservation of angular momentum, ensuring that the overall orbital path remains stable over long timescales. Despite these changes, the average orbital speed remains consistent when measured across a full revolution around the Sun. This orbital motion is not experienced directly by observers on Earth, because the entire planet atmosphere and surrounding environment move together as a single system. Everything on Earth shares the same velocity vector relative to the Sun, meaning that there is no internal sensation of this rapid movement through space. Instead, the effects of this motion are observed indirectly through astronomical measurements and the changing position of celestial objects in the sky over time. Earth's orbit lies within the plane of the solar system, a flattened region defined by the angular momentum of the original protoplanetary disk from which the planets formed. This alignment reflects the conservation of rotational motion from the early stages of solar system formation. The near-circular nature of the orbit is a result of long-term gravitational interactions and energy dissipation during planetary formation, which gradually settled the planets into stable trajectories. The velocity of Earth around the Sun is significant on a physical scale, reaching tens of kilometers per second. This motion is far faster than any human-scale movement, but remains stable and predictable due to the consistent gravitational pull of the Sun. As Earth orbits, it also carries its atmosphere, oceans, and magnetic field, along with it maintaining a coherent system that moves through space as a unified whole. Earth's orbital plane is slightly tilted relative to its rotational axis, creating seasonal variations in sunlight distribution as it moves along its path. This tilt does not affect the speed of orbital motion, but influences the angle at which solar radiation reaches different parts of the planet. Over time, this combination of orbital motion and axial tilt produces cyclical patterns that shape climate and environmental conditions on Earth's surface. The orbit itself is not perfectly fixed. Gravitational interactions with other planets, particularly Jupiter and Venus, introduce small variations in Earth's orbital parameters over long timescales. These variations are predictable and contribute to long-term cycles in Earth's climate system. However, the overall structure of the orbit remains stable due to the dominant gravitational influence of the Sun. As Earth moves through its orbit, it also participates in the larger motion of the solar system around the Milky Way. This layered motion means that Earth's path through space is not a simple closed loop, but a continuously advancing trajectory through the galaxy. While Earth completes each orbit around the Sun, the entire solar system shifts position within the Milky Way, creating a helical path on a much larger scale. This combined motion demonstrates how local and galactic dynamics are interwoven. Earth's orbital velocity is defined relative to the Sun, while the Sun's motion through the galaxy adds an additional component to Earth's overall velocity through space. These combined movements produce a complex but stable system of motion that extends across multiple scales of the universe. Despite the high speeds involved, Earth remains gravitationally bound to the Sun, ensuring long-term stability of its orbit. The balance between gravitational attraction and inertial motion maintains the planet's trajectory over billions of years. This stability allows Earth to remain within a relatively constant distance range from the Sun, supporting long-term environmental equilibrium. Earth's orbital motion represents one of the most fundamental scales of cosmic movement, linking the surface experience of time and seasons to the broader structure of the solar system and beyond. It serves as a central reference point for understanding how motion accumulates across layers of gravitational systems, from planetary orbits to galactic flows. Earth's rotation defines a second fundamental layer of motion within the solar system, occurring independently of its orbital movement around the Sun. The planet spins around an internal axis that runs from the North Pole to the South Pole, completing one full rotation in a period that establishes the cycle of day and night. This rotational motion is a remnant of the angular momentum present in the early formation of the solar system, when dust and gas collapsed into a rotating disk that eventually formed the Sun and planets. The rotational speed of Earth varies depending on latitude. At the equator, the surface moves at its highest linear velocity due to the larger circumference of the planet at that point. As latitude increases toward the poles, the effective surface speed decreases, reaching zero at the poles themselves. This variation does not affect the overall rotational period, which remains consistent across the entire planet. The atmosphere and oceans are carried along with this rotation, creating a unified system that maintains coherence despite internal fluid motion. This rotation produces a clear separation between day and night across Earth's surface. As the planet turns, different regions face toward or away from the Sun, receiving or losing direct solar radiation. This cycle is not influenced by Earth's orbital motion in a direct way, but is instead a consequence of the planet's axial spin. The boundary between daylight and darkness shifts continuously across the surface, creating a dynamic pattern of illumination that remains stable over time. The rotation of Earth also gives rise to the Coriolis effect, a deflection in the motion of air and ocean currents caused by the rotating reference frame of the planet. Moving objects on the surface appear to curve relative to the ground due to this rotational influence. This effect plays a significant role in shaping large-scale weather systems and ocean circulation patterns. Although it arises from rotation, it does not change the underlying speed of the planet, but modifies how motion is perceived within the rotating frame. Earth's rotation is gradually slowing over extremely long timescales due to tidal interactions with the Moon. The gravitational pull between Earth and the Moon creates tidal bulges in Earth's oceans, which in turn exert a small braking force on the planet's rotation. This transfer of angular momentum causes Earth's rotation to decelerate very slowly, while the Moon gradually moves farther away. These changes occur over millions of years and do not significantly affect short-term dynamics. The internal structure of Earth plays a role in how rotational motion is distributed. The planet is composed of a solid inner core, a liquid outer core, a viscous mantle, and a solid crust. These layers rotate together as a system, although slight differences in motion can occur due to fluid dynamics in the outer core and mantle. These internal variations contribute to changes in the magnetic field and other geophysical phenomena, but the overall rotational coherence of the planet remains stable. Rotation also influences the shape of Earth itself. The planet is not a perfect sphere but an oblate spheroid slightly flattened at the poles and bulging at the equator. This shape results from the balance between gravitational forces pulling matter inward and centrifugal effects generated by rotation. The equilibrium between these forces defines the planet's overall geometry and contributes to variations in gravitational strength across different latitudes. From a broader perspective, Earth's rotation is part of the nested structure of motion that defines its place in the universe. While the planet spins on its axis, it also orbits the Sun, while the solar system moves through the galaxy, and the galaxy itself participates in larger cosmic flows. Each level of motion is independent yet interconnected, forming a hierarchy of movement that extends from planetary surfaces to the largest observable scales of the universe. The stability of Earth's rotation is essential for maintaining long-term environmental consistency. The regular cycle of day and night influences temperature distributions, atmospheric circulation, and biological rhythms. This stability is a consequence of conservation of angular momentum, which ensures that the planet's rotation persists, with only gradual changes over geological time. Earth's rotational motion represents one of the most immediate and fundamental forms of cosmic movement, experienced indirectly by all processes on the surface. It defines the rhythm of time on a planetary scale, and forms a stable rotational framework within which all local motion is embedded. The Earth-Moon system introduces a shared gravitational structure in which both bodies move around a common center of mass, while also participating in larger orbital motion around the Sun. This shared center of mass, known as the barycenter, lies within Earth, but not at its exact center, shifting slightly in response to the Moon's position along its orbit. As a result, Earth does not move in a perfectly smooth path around the Sun, but instead follows a subtle wobbling trajectory influenced by the Moon's gravitational pull. The Moon's orbit around Earth is not a simple circular path, but an elliptical trajectory shaped by the combined gravitational forces of Earth, the Sun, and smaller perturbations from other planetary bodies. This orbit is stable over long timescales, maintained by the balance between gravitational attraction and the Moon's forward motion through space. The Moon's distance from Earth varies slightly during its orbit, creating changes in orbital speed consistent with conservation of angular momentum. As the Moon moves around Earth, it causes a periodic shift in Earth's position around the shared barycenter. This motion is small compared to Earth's orbit around the Sun, but measurable, with precise astronomical instruments. The Earth-Moon barycenter system effectively behaves as a single gravitational unit when viewed from larger scales, with both bodies contributing to the overall motion of the system through space. The interaction between Earth and the Moon also generates tidal forces. The Moon's gravity pulls more strongly on the side of Earth facing it, creating a slight elongation of Earth's oceans, and to a lesser extent its solid crust. This produces tidal bulges that rotate with Earth continuously shifting due to the planet's rotation. These tidal interactions are responsible for the gradual transfer of angular momentum between Earth and the Moon. Over long timescales, this transfer causes Earth's rotation to slow slightly, while the Moon slowly recedes from Earth. This process is extremely gradual but persistent, reflecting the continuous exchange of energy within the system. The result is a long-term evolution of the Earth-Moon distance and rotational period that unfolds over millions of years. The Moon's presence also stabilizes Earth's axial tilt. Without the Moon, Earth's rotation axis would experience larger variations due to gravitational influences from other planets. The Moon's gravitational effect helps maintain a relatively stable tilt, which contributes to consistent seasonal cycles over long periods. This stabilizing influence is a key factor in Earth's long-term climate stability. The Earth-Moon system itself orbits the Sun as a single combined unit. While the Moon revolves around Earth, both bodies trace a shared path through space, creating a combined orbital motion that reflects their mutual gravitational relationship. This motion is superimposed on the larger galactic movement of the solar system, forming another layer in the hierarchy of cosmic motion. The gravitational influence of the Sun on the Earth-Moon system is stronger than that of Earth on the Moon in some respects, yet the Moon remains bound to Earth due to the structure of their mutual gravitational relationship. The system exists in a stable configuration where both Earth and Moon remain in continuous motion around each other, while being carried along their orbit around the Sun. The barycentric motion of the Earth-Moon system also contributes to small variations in Earth's velocity through space. These variations are minor compared to the overall orbital motion around the Sun, but are important for precise calculations in celestial mechanics. They reflect the fact that no single body in the system is completely stationary, and all motion is relative to shared gravitational centers. The Earth-Moon system represents a tightly linked example of hierarchical motion. It demonstrates how smaller-scale gravitational interactions are embedded within larger orbital structures. The Moon's orbit around Earth, Earth's orbit around the Sun, and the solar system's motion through the galaxy all combine into a layered system of movement that remains stable across vast differences in scale. This stability arises from long-term gravitational equilibrium. Despite constant motion, the system maintains consistent structure because energy and angular momentum are distributed across both bodies in a balanced way. The result is a dynamic but coherent system in which motion is continuous but predictable over long periods. The Earth-Moon relationship therefore serves as an intermediate level in the broader framework of cosmic motion, linking planetary rotation and orbital dynamics with larger galactic structures. It illustrates how motion is never isolated, but always part of a connected hierarchy extending from local systems to the universe at large. Within the thin layer of gases surrounding Earth, motion takes on a fluid and continuously shifting character as the atmosphere moves in response to solar heating, planetary rotation, and gravitational constraints. The atmosphere is composed primarily of nitrogen and oxygen with trace gases and water vapor, distributed unevenly across altitude and latitude. Although it is bound to Earth by gravity and rotates with the planet as a whole, the atmosphere is not rigid. It behaves as a dynamic fluid that constantly redistributes energy and mass across the planet's surface. The general co-rotation of the atmosphere with Earth means that on average the air moves with the planet's surface as it spins through space. This shared motion ensures that large-scale atmospheric structures remain anchored to Earth's rotating frame. However, within this overall motion, local variations occur due to differences in temperature, pressure, and humidity. These variations drive wind systems that transport energy from warmer regions near the equator toward cooler regions at higher latitudes. Solar heating is the primary driver of atmospheric motion. As sunlight reaches Earth's surface, it is absorbed unevenly depending on surface-type angle of incidence and atmospheric conditions. This uneven heating creates pressure differences that cause air to move from high-pressure regions to low-pressure regions. The rotation of Earth modifies these flows, introducing curved paths due to the Coriolis effect, which influences the direction of large-scale wind patterns. At the largest scales, atmospheric circulation organizes into distinct cells that span from the equator to the poles. Warm air rises near the equator, moves poleward at higher altitudes, cools and sinks at subtropical regions, and then returns toward the equator near the surface. These circulation patterns distribute heat around the planet and maintain a relatively stable climate system, despite continuous input of solar energy. The structure of these cells is shaped by both rotation and the spherical geometry of Earth. Within these global circulation systems, smaller weather systems develop. Cyclones, anticyclones, and jet streams form as a result of interactions between temperature gradients and rotational forces. These systems move across the planet's surface while remaining embedded within the larger circulation structure. Although they appear dynamic and complex, they follow predictable physical principles governed by fluid dynamics and thermodynamics. The upper atmosphere contains layers where motion becomes influenced by decreasing density and increasing exposure to solar radiation. In these regions, particles are more widely spaced, and interactions with incoming solar wind become more significant. The boundary between the upper atmosphere and near-Earth space is gradual rather than abrupt, allowing energy and particles to exchange between the two regions. This transition zone plays an important role in shaping atmospheric escape and long-term evolution. Despite this complexity, the atmosphere remains gravitationally bound to Earth. The balance between thermal energy and gravitational attraction determines how far atmospheric particles can move from the surface before being lost to space. Lighter gases at higher altitudes can occasionally escape Earth's gravity over long timescales, while heavier gases remain more tightly bound. This process contributes slowly to the evolution of atmospheric composition. The atmosphere also interacts with Earth's magnetic field, which influences the movement of charged particles in the upper layers. These interactions produce visible phenomena such as auroras, where energetic particles from space collide with atmospheric gases and release light. These effects are localized to polar regions where magnetic field lines converge and allow greater penetration of charged particles. From a motion perspective, the atmosphere represents a medium that both shares Earth's global velocity and contains its own internal dynamics. It moves through space as part of the Earth-Moon system, orbiting the Sun and participating in the broader motion of the solar system. At the same time, it continuously circulates around the planet, redistributing energy and mass in response to external and internal forces. The stability of atmospheric motion depends on the balance between incoming solar energy and outgoing thermal radiation. This balance maintains Earth's climate system within a relatively narrow range over long periods, while short-term variations in weather can be significant. The overall structure of atmospheric motion remains stable due to the constraints imposed by gravity, rotation, and energy flow. In this way, the atmosphere forms a dynamic but coherent layer of motion that is deeply integrated into Earth's overall movement through space. It is both a local system driven by planetary forces and a component of the larger motion of Earth as it travels through the solar system and beyond. Word count 1057, At the surface of Earth, motion becomes more immediate and locally variable as different reference frames interact within the rotating planet. The surface is not a single uniform platform, but a collection of regions that move together through space, while exhibiting slight differences in velocity depending on latitude elevation and local geological structure. All surface motion is ultimately constrained by Earth's rotation and orbit, yet within that shared motion, subtle variations emerge that define the physical experience of movement at ground level. Latitude plays a central role in determining surface velocity because Earth's rotation produces different linear speeds at different distances from the axis of spin. Regions near the equator travel faster through space than regions closer to the poles, not in terms of angular rotation, but in linear distance covered over time. This variation is a direct consequence of spherical geometry combined with rotational motion. Despite these differences, all points on the surface complete one full rotation in the same period, maintaining global coherence. Elevation introduces another layer of variation in surface motion. Points at higher altitudes are slightly farther from Earth's center of mass, which results in marginally higher linear velocities due to the increased radius of rotation. Although this difference is extremely small compared to the overall speed of Earth's rotation and orbit, it illustrates how motion is sensitive to position within a gravitational field. Even minor changes in distance from the axis of rotation alter the effective velocity of a point on the surface. The surface itself is divided into tectonic plates that move slowly over geological timescales. These plates drift across the semi-fluid upper mantle, driven by convection currents within Earth's interior. This motion is extremely gradual compared to other forms of movement, yet over millions of years it reshapes continents and ocean basins. The movement of tectonic plates adds a deep time layer to surface motion, extending the concept of movement far beyond human perception. On shorter timescales, surface motion is influenced by geological processes such as erosion, sediment transport, and volcanic activity. Rivers carry material across landscapes, winds move dust and sand, and glaciers reshape terrain through slow but persistent motion. These processes are driven by energy from the sun gravity and internal heat from Earth's interior. Each process contributes to the continuous redistribution of matter across the planet's surface. Human-scale motion exists within this layered system. Structures, vehicles, and living organisms all move relative to the rotating Earth, while simultaneously participating in its orbital motion around the Sun. From a physical standpoint, all human activity occurs within a constantly moving frame of reference. Even when standing still on the ground, a point on Earth's surface is moving through space at high velocity due to planetary rotation and orbital motion. The atmosphere interacts closely with surface motion, transferring energy and momentum through wind and weather systems. Surface features such as mountains and oceans influence atmospheric flow, while atmospheric motion in turn shapes surface conditions through erosion and deposition. This feedback between surface and atmosphere creates a dynamic system in which motion is continuously exchanged between solid and fluid components of the planet. Ocean currents represent another major component of surface-level motion. Driven by wind temperature differences, salinity variations, and Earth's rotation, these currents circulate water across the globe in large interconnected systems. They transport heat from the equatorial regions toward the poles, contributing to global climate regulation. Although oceans appear static from a distance, they are in constant motion at multiple scales, from surface waves to deep ocean circulation. The interaction between land, water, and atmosphere produces a complex pattern of motion that varies across the planet's surface. Some regions are relatively stable, while others are highly dynamic, shaped by active geological or climatic processes. Despite this variability, all surface motion remains embedded within the larger rotational and orbital framework of Earth. From a broader perspective, surface motion represents the most accessible layer of Earth's overall movement through space. It is the interface where cosmic motion becomes physically tangible through weather geography and human experience. Yet even this layer is only one part of a much larger hierarchy of motion that extends from planetary rotation to galactic flow. The stability of surface motion arises from the consistent physical laws governing gravity rotation and energy transfer. While local conditions vary widely, the underlying structure remains coherent across the entire planet. This coherence allows Earth's surface to function as a stable platform, despite its continuous movement through space at multiple scales. Beneath the visible surface of Earth lies a deeper layer of motion that unfolds over geological timescales, where the planet's rigid outer shell is broken into large tectonic plates that slowly shift across the upper mantle. This movement is extremely gradual compared to surface processes, yet it represents one of the most powerful shaping forces of Earth's long-term evolution. The lithosphere, composed of crust and uppermost mantle, rests atop a softer, partially flowing region that allows plates to move in response to internal heat and gravitational forces. The driving mechanism behind tectonic motion is mantle convection, a slow circulation of solid but ductile rock that behaves like an extremely viscous fluid over long periods. Heat from Earth's interior, generated by residual formation energy and radioactive decay, creates temperature differences that cause material in the mantle to rise in some regions and sink in others. This movement forms convection cells that gradually transfer heat from the deep interior toward the surface, while simultaneously dragging tectonic plates along their upper boundary. Where mantle material rises, it creates zones of divergence at the surface. Here, tectonic plates are pulled apart, allowing magma to rise and form new crust, particularly along mid-ocean ridges. This process continuously regenerates parts of Earth's surface, ensuring that the planet's outer shell remains dynamic rather than static. In contrast, where mantle material sinks, plates are forced together in convergent zones. These regions are associated with mountain formation, deep ocean trenches, and volcanic activity, all of which reflect the recycling of crustal material back into the interior. The motion of tectonic plates is not uniform. Different plates move at different speeds and directions, influenced by variations in mantle flow and interactions with neighboring plates. These differences create complex boundary interactions, including sliding motion along transform faults where plates move laterally past each other. Over millions of years, these interactions reshape the arrangement of continents and oceans, gradually altering the geometry of Earth's surface. Continental drift, a surface expression of tectonic motion, reflects the long-term movement of large landmasses across the globe. Continents are not fixed, but are carried on tectonic plates that slowly change position over time. This movement explains the historical rearrangement of Earth's land masses, including the formation and breakup of ancient supercontinents. The present configuration of continents is only a temporary arrangement within a much longer cycle of assembly and fragmentation. The mantle itself is not uniform. It contains variations in composition, temperature, and density that influence the pattern of convection. These variations can create localized upwelling zones known as mantle plumes, which rise toward the surface and may produce volcanic hotspots independent of plate boundaries. These plumes represent another form of internal motion, transferring heat and material from deep within Earth toward the crust in a focused but persistent manner. Despite its slow pace, tectonic motion has a profound impact on Earth's surface environment. It shapes mountain ranges, controls the distribution of continents, and influences long-term climate by altering ocean circulation patterns and atmospheric circulation through changes in geography. Over geological time, this motion continuously rebuilds the surface of the planet, ensuring that no configuration remains permanent. The interaction between tectonic plates also plays a key role in the carbon cycle. Subduction zones transport carbon-rich materials into the mantle, while volcanic activity releases gases back into the atmosphere. This exchange links deep Earth processes with surface and atmospheric conditions, integrating internal motion with surface and atmospheric systems. Over long time scales, this cycle contributes to the regulation of Earth's climate system. At the deepest level of this layered structure lies the boundary between the mantle and the core. Heat flow from the core into the mantle drives much of the convection that powers plate motion. Although the core is not directly accessible, its influence is evident in the continuous motion of the mantle above it. This internal energy source ensures that Earth remains dynamically active long after its formation. Tectonic motion represents the slowest visible layer of Earth's movement within the broader hierarchy of cosmic motion. While planetary rotation, orbital motion, and atmospheric circulation operate on shorter timescales, tectonics unfolds over millions of years, shaping the long-term evolution of the planet. It is a deep, persistent movement that operates beneath human perception, yet defines the structure of Earth over geological history. This internal motion remains stable over immense timescales due to the balance between heat production, heat loss, and gravitational forces. The result is a planet that continuously reshapes itself from within while maintaining overall structural integrity. In the broader context of cosmic motion, tectonic activity represents the deep interior layer of Earth's participation in the universe's hierarchy of movement. At the deepest accessible layer of Earth's internal structure, motion continues within the planet's core, where extreme pressure and temperature create conditions unlike those found in any other region of the planet. The core is divided into a solid inner region and a liquid outer region, both composed primarily of iron and nickel. The outer core remains in constant fluid motion, driven by heat escaping from the inner core and the gradual cooling of the planet over time. This motion is slow on human timescales, but highly significant in shaping Earth's magnetic and dynamic behavior. The movement within the outer core is not uniform, but organized into complex circulation patterns, influenced by rotation, heat transfer, and the Coriolis effect generated by Earth's spin. These flows consist of rising and sinking streams of electrically conductive fluid metal. As the liquid iron moves, it generates electric currents, which in turn produce magnetic fields. This process, known as the geodynamo, is responsible for creating and maintaining Earth's global magnetic field. The magnetic field extends far beyond the core, forming a protective region around the planet that interacts with solar wind and charged particles from space. This field is not static, but continuously reshaped by the motion of fluid within the outer core. Changes in flow patterns can lead to gradual shifts in magnetic intensity and orientation over long periods. These variations are recorded in geological materials and provide evidence of the long-term motion occurring within Earth's interior. The inner core, though solid due to immense pressure, is not entirely static. It is thought to rotate at a slightly different rate than the surrounding mantle and outer core, creating subtle, differential motion within the planet's deepest region. This relative motion is extremely small but measurable through careful analysis of seismic waves passing through Earth. It reflects the layered nature of internal planetary dynamics, where even solid structures participate in slow but continuous movement. Seismic waves generated by earthquakes provide the primary means of observing internal motion within Earth. As these waves travel through different layers, they change speed and direction, depending on the density and composition of the material they pass through. By analysing these variations, scientists reconstruct the internal structure and motion of the core and mantle. This indirect observation reveals a deeply dynamic interior that is otherwise hidden from direct view. Heat flow from the inner core to the mantle drives much of this internal motion. As energy moves outward, it creates gradients that sustain convection in the outer core and mantle above it. This energy transfer is slow but continuous, maintaining Earth's long-term geodynamic activity. Without this internal heat, the planet's motion would gradually diminish, leading to a more static interior structure over geological time. The interaction between the core's motion and the mantle above it links Earth's deepest internal dynamics with surface and atmospheric systems. Magnetic fields generated in the core influence space weather interactions, while mantle convection shapes surface geology. This connection demonstrates that motion within Earth is not isolated by depth, but forms a continuous system spanning from the inner core to the atmosphere. In the broader context of planetary motion, the core represents the innermost layer of dynamic activity within Earth's overall movement through space. While orbital and rotational motions define the planet's external trajectory, the core defines its internal energy-driven evolution. Both are part of a unified system in which motion exists at every scale, from the movement of galaxies to the circulation of molten metal deep within planetary interiors. As Earth continues its journey through the solar system and the galaxy beyond, the internal motion of its core remains active and self-sustaining. This motion supports the magnetic field influences geological activity and maintains the structural evolution of the planet over billions of years. It represents the final inward layer of the hierarchical structure of motion described throughout this journey, completing the transition from cosmic expansion to planetary interior dynamics. At this deepest level, motion is no longer about visible movement through space, but about continuous transformation within matter itself. Even in the absence of external observation, the planet remains dynamic, shaped by forces that operate across time and depth. This hidden motion completes the full spectrum of Earth's journey through the universe, from the largest cosmic scales to the most intimate internal processes.